So I'm sure you've heard of Bitcoin. Bitcoin is a cryptocurrency that uses proof of work to secure its network, which is a process that people often refer to as mining. Modern mining machines are called ASICs, application-specific integrated circuit, which means that the processor is a piece of silicon that's designed to only mine Bitcoin and nothing else. As a result, these ASICs are incredibly fast at mining Bitcoin. I wanted to see for myself, how does mining actually work? So in this video, I set out to write a Bitcoin miner completely from scratch. The first step is to set up my C++ development environment in Visual Studio Code. And then, as with every project, write a starting Hello World program. Then, I wrote a method for C++ to turn a hexadecimal string into bytes in the computer's memory, so that we can provide input to the computer in a human-readable format. Now I could set out writing the miner. Bitcoin mining is built from SHA-256, a hashing algorithm designed by the NSA. The Ethereum Foundation provided a very nice document describing how SHA-256 works, which was really useful in figuring out in detail how the algorithm functions. First, we take our data, L bits in length, and pad the message into 512-bit blocks, the end of the final block containing the length L as a 64-bit number. For each of these end message blocks, we run the main loop algorithm, which hashes the previous loop's output into the next message. We need an initial value to combine with our first message block, and for this we use the constant values found by taking the fractional parts of the square roots of the first 8 primes. Now we can write our main loop. First, we initialize registers A through H with our previous hash values, and then 64 times we run the SHA-256 compression function, which consists of computing specific bitwise functions on our registers, then rotating each of our registers and adding these computed values in specific ways. Part of this includes adding the W_J value, which is how we include our new message block into the current hash's step. The final HI value, after we've included every message into our hash, is the output value of our SHA-256 algorithm. After I'd written all of these, the SHA algorithm was ready to test. I wrote another helper function to convert a hex string to int array to ensure our input is in the correct format for the SHA function, and another function to print out memory in a hex format. I had some issues with endianness, which is the order that the bytes are stored in memory. Do we store the most significant byte at the left or the right hand side of our memory range? But after fixing this, I was able to successfully hash the word test and compare this with an online SHA-256 hashing website. Now that we have a functioning SHA-256 algorithm, we can write our block hasher. For this, we need to understand a bit more of how mining works. When we're mining a block, we're continually running our SHA-256 algorithm with one number changed each time. This number is called the nonce, a cryptographic term meaning number that is used once. For each value that we hash, we get a completely different 256-bit output, and we compare this to our difficulty value. If our output is smaller than our target difficulty, then we can count the block as solved. In simpler terms, this can be seen as getting a certain number of zeros at the start of the hashed value. Due to the irreversibility property of a hashing function, we can't get back to the input values from a hash that we may seek. So the only way to find a nonce that has the required number of zeros in its output is to repeatedly hash order of 2 to the power of n times, where n is the number of binary zeros that we seek. Here's a demonstration to show that we're successfully verifying the hash of the Bitcoin Genesis block, which was the first block that was ever mined in 2009. When mining Bitcoin, we include a few key things into the block header, which is the information that we hash. We take the version of the block, the hash of the previous block, the Merkle root, which is the aggregation of all the transactions that are included in this block, the current timestamp, and the nonce. The key to this is the previous block hash, as this is what makes it a block chain. This then means that if someone tries to alter a block further up in the chain, then it will change the hash of the block, hence the hash is no longer a solution to the difficulty problem. This also changes the next block hash, and so on, with every block subsequent to our tampered block being broken. So the network will no longer see these blocks as having valid proof of work. Since we know what our nonce should be for the Genesis block, we can now test our mining algorithm by letting the start nonce be slightly lower than the nonce that solves the block, and run the miner to see that after a few attempts and incrementing the nonce by 1 each time, the miner finds the correct nonce that solves the block. I also wrote a bit of code to time how long it takes to do 10,000 hashes, so we can get a rough estimate for the hash rate. We can see here we're mining about 60 kilohash per second. I hope you've enjoyed this video and you've learned something. If you'd like to look at more detail at how this works, find a link to the source code in the description. Thank you so much for watching.